Okay, welcome to lesson 8.4 and 8.5. We're going to do a combination lesson, and in this lesson we're looking at the three different forms of the equation of a plane. So the vector, the parametric, and the Cartesian equations. So in this diagram here, we've got four different pictures of a plane. So the plane is the rectangle, and we're talking about different ways that we can determine a plane. Like, do we have enough information? So for instance, if I gave you just 1 point, that's not enough information to determine the equation of a plane, because you can imagine, like if you had a piece of dust floating in the air and a sheet of paper, how could that sheet of paper touch that piece of dust? An infinite number of ways, right? We could rotate that piece of paper around the point. It's not enough information. Same thing if I only gave you 2 points. Again, I could be rotating the piece of paper around the 2 points as if the 2 points created a line, and that piece of paper could be spinning around that line. And again, I don't have enough information to fix the plane in one position. So ways that I can determine the line is, or just the equation of a plane, is if I had a line and another point that's not on the line. Then that's going to there's only one way for me to lay a piece of paper across this line that also touches the point. Another way for me to do it is if I had three non-collinear points. So that's going to be important, right? They can't lie in a line, all 3 points. Otherwise, I really just have one line, and I would have something just like this, but without this extra point off to the side. So they can't all be collinear. The third way I could do it is to have two intersecting lines like this that cross each other. And then the fourth way is if I had two parallel lines that are non-coincident, so not on top of each other. They do have to be separate, and that'll also uniquely determine the plane. Now, in our previous lessons this chapter, we were looking at finding the equation of a line, and to find the equation of a line, we used a point and a direction vector. To find the equation of a plane, the first two formats that we're going to look at are very similar to some of our equations of a line. We're going to look at the vector equation and the parametric equation. The difference, though, is that we're going to be using a point and any two non-collinear vectors. And sometimes you're going to hear me talk about those collinear vectors, and I'm going to use the phrase direction vectors because they kind of remind us of it. So I'll use that term sometimes, but it's any two vectors that are non-collinear. And so my first equation of a plane is, again, I've got the r vector is equal to r naught plus, and so r naught, again, is going to be the vector from the origin to some point on the plane. So the head of the vector is a point on the plane. You could think of r naught as a point if you want. And then we're going to have two non-collinear vectors, or two direction vectors. So we'll have two parameters for that. So s times the first direction vector, and then t times the second direction vector. So you see here, we're using lowercase a and lowercase b as our direction vectors instead of m. The parametric equation of the plane, very similar to parametric for a line. I'm just taking this equation here and taking it apart in terms of the x, the y, and the z. So I'll have the x naught, y naught, z naught from the point. And then I'll take the parameter s and multiply it by the three coordinates of the first direction vector a. So direction vector a is defined as a1, a2, a3. So a1 is the x coordinate. I'll put it in the x equation multiplied by the parameter s. And then same thing for vector b. It's defined as b1, b2, b3 for the x, y, and z. And so I'll take those out and multiply them by the parameter t that it was being multiplied by in the vector equation. And then don't forget to define your parameters. We've got s and t. They're both elements of the real number system. The third way that we can define the equation of a plane is the Cartesian equation of a plane. So you'll notice that symmetric is the one that's missing here. We don't have a symmetric equation of a plane. The Cartesian equation of the plane is also sometimes called the scalar equation of the plane, and it looks, again, very similar to the Cartesian equation of a line. It's just that now we also have this CZ component of the equation. And in this equation, because I've got an x, a y, and a z, the normal vector, and again, because I'm in 3 space, is going to be a, b, and c. So here I'm using capital A, b's, and c's to define my normal vector n. And so again, in finding the equation of a plane, whenever you use the n for your vector, I'm going to be assuming that you're talking about a normal vector. And this normal vector is going to be perpendicular to all of the vectors in the entire plane. So again, if I was thinking about this plane here, any vector that's perpendicular to the plane could be used as a normal vector. Now remember, we always slide those vectors in and attach them to the origin. So that normal vector will be perpendicular to all of the other vectors in the plane, whether I'm talking about the vector that represents line 2 here or the vector that represents line 1, my normal vector would stick perpendicular out of this plane, so it would be perpendicular to everything there. All right, example 1. So again, one of the trickiest parts of this chapter is deciding what am I trying to figure out, picking out that equation, and then what information am I given, so how am I going to get there? Now, I want a vector, parametric, and Cartesian equation for the plane that contains these 3 points. Now, in order to find a vector in a parametric equation, I need 2 vectors that are on the plane. And so we usually call those A and B. So that's what I'm thinking here. And then in order to find the Cartesian equation later on, I'm going to do that one second, I'm going to need a normal vector. So I'm just kind of keeping that in the back of my mind. So first, coming up with those 2 vectors A and B to define the vector and parametric equations. So I need to come up with any vector A that's on the plane. And I've got 3 points. So all I need to do is join 2 of these points and I'll create a vector or a direction vector that's on the line. Now I have many choices. I need to do it twice. So my choices are, I'll just do this over here, I wouldn't write this down. My choices for vectors are PQ, PR, and QR. And I could do the reverse of that. Now being careful, when I pick 2, I can never pick these 2 because those guys would be coincident, right? So I couldn't pick this pairing, but I could flip any of these vectors around. And so there are multiple choices. There's going to be multiple answers here. But again, you can't pick these 2 together. That would be bad. But I could pick these 2 together. That would be fine. Or I could pick these 2 together. This would be fine as well. I'm going to do PQ and PR. Those are going to be my 2. So to find a vector that starts at the tail P and ends at the head Q, we subtract the head components minus the tail components. So 5 minus 3 for the first component, and then 2 minus -2, and then 0 minus 1. For our second vector that lies on the line, again, I said I'm going to choose PR, but there are other choices. You're going to find it kind of tricky to check your answers for this chapter because of that. Oops. And so I'm using R as the head, so I'm going to do 6 minus 3, and then -3 minus -2, so that's -3 plus 2, and then 4 minus 1. Okay, and again, you could have had a different combination. But these are the 2 vectors I'm going to choose. Now to come up with a vector equation of a plane, I also need a point on the plane. I have 3 choices. So again, somebody could choose that R0 is going to be OP. So I'm using O as the origin, going to P. Or somebody else could choose OQ. Or somebody else could choose OR. So lots of different choices here as well. I'm going to choose R0 is equal to OP. And so that's going to be just 3, -2, 1. And I'm okay if you don't want to write this step here. That's fine. Okay, now we're going to put this all together. We've got all the information that we need. So vector. I know that the vector equation, I'm just going to rewrite it from above, but you don't normally need to write this. Starts out like this, so I'm going to define mine. I only deal with one line in this question, so I'm just using R. I don't need like a subscript 1 or 2. And I'm going to fill in my R0 plus the first parameter times my A vector plus the second parameter times my B vector. And then don't forget to define the fact that S and T belong to the set of real numbers. And this is a comma here, so like this piece here where you define that could go underneath if you were looking to save some space. It doesn't really matter. All right, so next we're going to do the parametric equations, which are very much related to the vector equation. So we're just taking this apart. We're going to take the x coordinates out of here. And you're often going to see that we define planes, and you saw this on the diagram up here maybe, that they have this little pi symbol. And so if I have different planes, I would say pi 1, pi 2, like with a subscript. So I'm going to define the plane here just because you'll sometimes see this. So pi, and again, if I was dealing with multiple planes, I would add subscripts. Pi is defined by x is equal to, and I'm just going to grab all the x components out of here, and I have to remember to multiply by the parameters as I do that. And then I'll do the same thing for y. So now I'm looking right after the highlight at -2 plus 4s minus t. And then looking at the z, so looking at the last one, I've got 1 minus s plus 3t. And then remembering to define my parameters as well. And again, you can do it off to the side here, or you could do it underneath, it doesn't really matter. All right, the last thing we were asked to do in this question is to come up with the Cartesian equation. Now, we don't have everything we need for the Cartesian equation. For the Cartesian equation, we need a normal vector to the plane. Now, whenever you have a question where you already have two vectors on the plane, I want to see you use the cross product, right? If I have two vectors and I want a third that's perpendicular, I use the cross product. So again, I wouldn't normally write this in pink here. This is more just for your notes. Okay, so for the Cartesian equation, I need a normal vector. And to come up with that, I'm going to take my vector A from above and cross it with vector B. So if you like that memory trick, you're going to take the A coordinates, and the B coordinates, just ignoring the first ones and the last ones. I'm doing a double stack here. And I'm going to cross them. So I'm just going to rewrite them here so that they're on my screen, but you don't need to do this. So we're going to start to cross. And we're looking first at going from A2 to B3. So 4 times 3. And then we're going to subtract A3 times B2. So we get +1 there when I do -1 times -1. And now we're going the third one times the first one. So -1 times 3 minus, and then the first one times the third one, 6. And then we're going to do the first one times the second one, so 2 times -1, minus the second one times the first one, so 12. And so for my normal vector, I end up with this. And there are many different normal vectors that you could choose, but this is the one I'm going to be looking for, the one that results from the cross product of the two given vectors. All right, so now I'm going to set up my Cartesian equation of a plane. Remember that it looks like this. And I know that the normal vector represents the A, B, and C. So I'm just left with having to find D here. So I'm going to sub in a point from above for my X, Y, and my Z. And you can choose any of the 3 points, P, Q, or R, the original points in the question. So again, there's a bit of choice here. I'm going to choose Q because it's got a 0. So like that's less math for me to do, and there's no negatives, but you could pick any point that you like. So I'm going to plug that in. And so here I get 55 minus 18, so that gives me 37 plus 0 plus d. And so I see that d is equal to negative 37. And remember, there are multiple answers here, so your answer might not always match the textbook. You can always email me if you wanted to double check. All right, example 2, we're looking at a plane. They're calling it pi. The plane pi has this as its equation. Determine the point of intersection between pi and the x-axis. So remember that we're thinking about, we've got like, let me just grab a picture of a 3D. So I've got some plane out there, right? So perhaps the plane, I'm trying to figure out how I could draw this for you like this. So perhaps the plane looks like this, right? It's kind of on an angle going back, and maybe it crosses through the x-axis. I can't tell from this picture exactly, but maybe it crosses through here, right? And it's just coming through at one point on the x-axis. There are other possibilities for how planes and lines can intersect. We would look at that in chapter 9. But that's kind of just a quick visual. I wouldn't expect you to be able to visualize that or think about all the possibilities in this chapter. But that's what we're looking for. So what I'm going to think about is, well, what will that point of intersection look like if I'm on the x-axis? So a point on the x-axis has specific coordinates. It can't have a y coordinate or a z coordinate, right? Those both have to be z. So this is what I know my answer looks like. Now, in my equation, I've got it in vector form, but here I know information about x, y, and z. So I'm going to take my equation and pull it apart so that it's in terms of x, y, and z so that I can compare them. So I'm going to pull it apart in terms of my parametrics. So again, I'm taking my first components and putting them in with the x equation. So 6 plus 0 s's, I don't need to write that down, plus 2t. And then y will be the second. And then z will be the third. And then they've already defined S and T up here. I'm going to redefine it down here for my parametric. Okay, so now what we can see here, I've got these 3 different equations. What I'm going to do is sub my point. I know that I need 0 for y and z, and that's going to help me figure out my x coordinate. So, and you could sub in a for x at the same time if you want, or I'm going to come back to that later on in my case. So in my first equation here, I'm going to get that 0 is equal to negative 2 plus 3s plus 2t. And then in my second equation, grabbing my z equation, z value has to be 0. And then I'm going to be able to figure out what the values are for s and t. Now, what I've got here is an equation with I've got 2 equations with 2 unknowns, so this is a system of equations. So I'm going to call this equation 1 and this equation 2, and I'm going to either use substitution or elimination to solve for one of these variables. So I'm going to rearrange number 2 here because it seems pretty easy with just a 1 in front of the s. And you can do that underneath here. It doesn't really matter. I'm going to rearrange 2, and I get that s is equal to t plus 3. And I'm going to sub that into 1. So in equation 1, I'm just replacing the s with t plus 3. And so I see here that t is equal to negative 7/5. Now that I have my t value, remember my goal here is to come up with the x value. So I could go back in a different question. They might need the s number as well, in which case I would sub my t equals negative 7/5 into like equation 2 or equation 1 to solve for s. In this particular question, I actually don't need s, so I'm going to skip that step and just sub it into that equation. So we've got 6 plus 2 times the t value. And so here I get minus 14/5. And so 6 in terms of fifths would be 30/5. And 30 minus 14 gives me 16/5. So therefore, all right. The next part here, we're talking about the angle between two planes. So we know that if I have the angle, between the two normal vectors, so I want to imagine that when I have the two sheets of paper, how they cross into each other. I think I actually have a diagram of this that I'm going to upload. I don't have it ready here for me, but if I have the two sheets of paper, so let's say that they kind of look like this, then there are two normal vectors coming out like this. I do have a diagram on Google Classroom that I want you to go take a look at. The normal vectors would stick out like this, and the angle where these two normal vectors meet is actually going to tell me the angle where the two planes meet as well. So we're just gonna, if you don't want the visual, just trust me here. If I want the angle between two planes, then I use the dot product between the two normal vectors. All right, so I've got my two planes here, pi 1 and pi 2. I want to find the angle between the two planes. So in order to do that, I need to come up with their normal vectors. So for pi 1, the normal vector, I'm going to call it n1. And I'm just grabbing the coefficients in front of x, y, and z. And then for pi 2, I'll do the same thing. I'll come up with my second normal vector. So normal vector for this plane is 3, negative 1, 2. And then I can find the angle in between. So I'm going to take the two normal vectors and plug them into my dot product formula. So taking the dot product of these two vectors, I'm just taking the x components and multiplying them, and then adding, take the y components and multiply them, and then adding, take the z components and multiply them. And then to find the magnitudes, you could do this off to the side if you like, and then just bring the answer in here. To find the magnitude of vector n1, I'll take each component and square it. And then to find the magnitude of vector n2, we'll take each component and square it. And so this is going to simplify. On top we've got 7, and then we've got root 6 times root 14. And then we can solve for the angle by doing cos inverse. And again, it depends on your calculator how much you need to simplify this fraction before you type it into your calculator. So you might want to do the 6 times 14 and put that under one root. Don't forget though that it is rooted. You're going to type that in. Make sure you practice this with your calculator and make sure that you can get about 40 degrees. Now that's going to be the acute angle where the two planes meet. Don't forget that if you wanted the obtuse angle, you would just take this number and subtract it from 180. Or if you had a question that came out with an obtuse angle and you wanted the acute, subtract from 180. Okay, good luck with your practice. Again, I think a lot of the trouble here is just sorting out what information am I given and what do I need in order to come up with this certain version of the equation of a plane. Have fun.